If you recall, Faraday's original experiment involved what is called mutual inductance. There were two coils, wrapped around an iron core, and then the B field generated by the one coil induced a current in the other coil, or the change in the B field generated by the one coil. Now, a single coil can have a similar effect, and that's called self-inductance. So if you have a coil of wire, say you have like the solenoid that I used this to when I was initially talking about Faraday's law and inductance, and let's say there's a current that is running through that coil. So let's say we've got a battery and it runs, and so it runs a current through this coil of wire. Okay. Well, what happens then? This coil of wire, as the current runs through this coil of wire, that generates a magnetic field, right? Because we've got a current moving around in a circle, so that'll generate a magnetic field. As I've drawn it, we've got current moving this way, and so there will be a magnetic field pointing to the right as it goes along. Well, if we throw in a switch, pretend I made a switch over here, and so initially there's no current. I throw the switch, now there's some current, and the current starts flowing, and as the current flows, this B field increases. So as this B field is increasing, that means that the flux through this coil is increasing to the left, which means that there will be an induced current in this coil. From its own B field, there will be a current induced to counter this change in flux. There will be a current produced to create a B field to the right, which means a current going in the opposite direction. And in this case, there's a current going to the right. There will be a current going to the left to generate that B field in the opposite direction. Now that's confusing because this battery causes the current to go this way, but then it causes the current to kind of oppose it, and that's what is called self-inductance. So this coil, there can be a current flowing through it, but this coil tends to resist a change in current. It's only when the current's changing that the B field, or that there's an induced EMF, an induced current. So it resists the change in current, and that's when something does that, that's called an inductor. So the coil tends to resist changes in current, even if you have ideal wires that don't have any resistance. Now we know the magnitude of an induced EMF is N delta phi over T. I was thinking d phi dt, and so I started to write the d. Sorry about that. And the wire itself, generates the B field that causes the change in flux. And the change in flux is proportional to the rate of change of the current. It's proportional to the change in the current over time, or it's actually di by dt. It's proportional to that, and what that constant of proportionality is. So we can say that the EMF is equal to the change in current, I should say absolute value, change in current over time times some constant. And that constant, capital L, is what's called the inductance of the wire. All right? And so if we just look at the relationship between these two equations, we can say that our L times delta I over T equals N times delta phi over T. And rearranging it gives us that this inductance is equal to N times delta phi over delta I. Oops, not parentheses. That should be an absolute value sign. All right. Inductance is measured in henries, which is a capital H, and 1 Henry is 1 volts second per amp. So that's a fairly complex unit, but oh well. Generally, inductances fall in the millihenry range. So now, a typical example of an inductor is a solenoid. So in a solenoid, we figured out a while back that the magnetic field in the solenoid is mu naught Ni over L, or mu naught little n times I, where L, I'll use a script L because it is the length of the solenoid, not to be confused with inductance, where little n is just the number of turns per length and big N is the number of turns. So the magnetic flux through a solenoid is just mu naught Ni over L times the area, cross-sectional area of the solenoid, right? So if we turn on a solenoid, we say our initial current is 0, then we get that the inductance of said solenoid is, well, it's N times delta phi over delta I. So you've got N times our delta phi, well, our phi, once we get a current I, is mu naught Ni over L times area. And our initial was 0, so our delta phi we can just say is our phi. And if we close the switch again, our delta I we can just say is I. And so then the currents cancel out, and we just get a mu naught n squared A over L, which we can also write as mu naught little n squared A times L. And so this is the inductance of a solenoid. It's the quantification of how much it resists that current turning on. So let's take an example problem. Let's say a solenoid with 500 turns is 8 centimeters long, current is increased from 0 to 2.5 amps in 0.35 seconds, and the EMF generated is 0.025 volts. I'm going to find the inductance and the cross-sectional area of the solenoid. Well, the inductance, actually I don't know if we even need the EMF, but the inductance we can find just by applying the formula. Inductance is mu naught n squared. Oh, we need the cross-sectional area there. Okay. We know that the EMF is equal to L times our delta current over time. We also know that our inductance is equal to, we also know that the inductance is equal to mu naught n squared area over L. So this EMF is 0.012 volts, we do need it, and that's equal to the inductance times the change in current, which is just 2.5 minus 0 over 0.35, and so our inductance is equal to 0.00168, which is about 1.7 millihenries. And then if we go over here, then the cross-sectional area of the solenoid is equal to the length of the solenoid times the inductance over mu naught n squared. We can plug in values. The length of the solenoid is 8 centimeters, which is 0.08. The inductance of the solenoid is at 0.00168 we just found. And then mu naught is 4 pi times 10 to the minus 7th. And the number of turns is 500 squared. So we can find that the cross-sectional area of our solenoid is 4.278 times 10 to the minus 4th, which is about, I'm kind of running out of space, I hope you can still see this, 4.3 times 10 to the minus 4th meters squared. Allow me to zoom in. Aha! So now you can actually see what I wrote down in the bottom corner there. So that's just an example of using a solenoid as an inductor and the sort of problems we can do with that. We will next time be talking about how inductors function in circuits, and how they're related, what they're used for in circuits and how they work in circuits, and as well as what they do when they're paired with resistors.